Cellular networks are very successful. The 5th generation is being rolled out, and the number of subscribers to cellular networks is growing tremendously. Researchers are working on the 6th generation. And what makes the 6th generation better? Subscribers can communicate faster, they get higher bit rates. We can accommodate more subscribers per unit of area, so we need to improve the way that the cellular system performs. And how can that be done? In another video I discussed the concept of cell-free networks. And I got a very interesting discussion from which I learned that some people see a cell-free network as a network in which the physical layer does something very special to make sure that in different cells the base stations can cooperate in reaching a subscriber somewhere in between. But others see the cell-free network as a networking activity where probably even AI coordinates the activity among base stations. Now, regardless of whether it will be cell-free and how it will be implemented, I think it is a good idea to discuss a little bit in more detail how cellular networks were envisioned in the beginning, in the 80s, so to say, and how things developed, and also how things changed and how we're still designing the system. Let's go back to history. The idea was that we need a telephone network to make circuit-switched calls. So a subscriber needed to have a continuous connection for a certain period of time. And GSM, a base station, could carry 8 phone calls at the same time. In the Berkeley project InfoPad, we started to look in wireless multimedia communication. But that required packet-switched networks, where you send a bit of data, a web page, a piece of video, and then the connection is inactive for some time, and you need to reactivate that later on. So the whole discussion is no longer about circuit switching, but it is about packet switching. Still, if we want to use the concept of cellular networks, we may have to apply some changes to that. So the whole discussion in a cellular network is how much interference can you tolerate in order not to disrupt a phone call. But if we change that to packet communication, then the question is different. We have packet queues in all the base stations. We need to transmit packets as quickly as possible to all the users in that cell area. And probably one of the better design criteria then is how can we minimize the delay in the network such that we serve all the users as fast as possible. And that is a different requirement as optimizing an interference-free call for a particular subscriber at the cell edge. Now, does that relate? Well, you may think that the fastest way to empty the buffer, to empty the queue in the buffer of the base station, is to have a clear channel. Because then the chances of a collision and the chances that you need to do a retransmission are very low. The probability of success the first time is much larger if you have a clear channel. All right, yes. But the total amount of spectrum is limited. So if we achieve a clear channel by prohibiting the use of the same frequency in neighboring cells, and we only reuse a certain frequency at a large distance, we need many frequencies. And if we have a limited amount of total spectrum available for our service, then we have to chop it up in a lot of tiny pieces. And each of the cells only has a very limited bandwidth. And it needs to reserve the other bandwidth for transmissions in the other cells. To reserve. To have it unused basically for a lot of time. So the question is, where is the balance? And what would be an optimal reuse factor, an optimal reuse distance in a packet switched system? So it may be good to use the entire bandwidth in each and every cell, which would mean that in every cell the transmissions can be very fast. You empty your queue very rapidly, the delay is short. And by doing that, you don't cause interference during most of the time to the other cells. So it is interesting to analyze that in more detail. One of the important aspects there is that the subscribers at the cell edge are at a disadvantage. And let's, for time being, make the assumption that they are served by a single base station only, the base station of their cell. That base station has to do many transmission attempts if there is a lot of interference. So if we use the same frequency everywhere, curve A applies. Many retransmissions, particularly for the terminals at a distance. If we go to curve D and E, we consider the situation that we make a spatial reservation, that we split the spectrum such that there can be a large reuse distance, that we have a clear channel, but every cell only has a limited part of the total bandwidth. The number of retransmission attempts is much lower, but the bandwidth per cell is small, and transmission goes slowly. You only make one attempt, but you do that slowly. Now, where is the optimum? And for that, we need to model the delay here as an MG1 infinity queue. The idea is that packets come in according to a Poisson process randomly, but the service time is a bit tricky. That is not the usual kind of thing. That is where the number of retransmission attempts really count. So let's use QR, the number of attempts that we use, the probability that a transmission is successful. Then 1 over QR is the number of attempts that I have to make. And that changes as a function of R. So I average 1 over Q over the spatial area of the cell, from 0, very close to the base station, to R, which is at the cell boundary. We not only need to have the first moment. In an MG1 queue, we also need to have the second moment. It's not too hard to write up an expression for the variance and for the second moment of the number of attempts that we have to make. And with that, we get the expression for the delay in an MG1 queue. You can just read the paper in which we describe it to get the details. Now this allows us to calculate the delay, the time that it takes from a new packet to come into the buffer until it is transmitted and finally is successfully transmitted. And that delay, of course, also depends on how fast we can transmit, thus on how much bandwidth we have in every cell. On the horizontal axis is the arrival rate, the number of packets on average that come in per cell. On the vertical axis we have the delay, and C is the number of different frequencies that I'm assigning. So CS7 is the typical cellular network choice. We have 7 different frequencies, and that really allows that neighboring cells do not use the same frequency. We can also have cell sizes of 4 or 3, but an interesting result here is for C is 1. That is, the same frequency is used everywhere. And that's a much better choice. It looks here, the delay is much shorter. So it is better to let all the base stations use all the bandwidth, which causes a lot of interference. But since they have so much bandwidth available, they can finish their queues very rapidly, and that limits the delay. And now you would say, is this a stable system? Because it could be that there are some subscribers at the cell edges and they need to have a lot of retransmissions and they continue to get interference. And then we have to do something, because in that case we may be clogged up in a system where just congestion and interference and retransmission is filling the entire bandwidth and the successful throughput is very low. And that is something that we can resolve at a network layer, because what we can do is just do a first transmission attempt. If it is not successful, you do a retransmission attempt, but you take some precautions. Only at that moment you ask your neighboring cells to be silent, such that in the cell where you need a clean channel to make sure that the second transmission attempt is successful, you do get that clean channel because the neighbors are silent. And you could agree on a scheme on which we could organize that, and that could be done in the time domain. So we define time slots. There is a hidden frequency reuse pattern. For instance, C is 3 in this case. And when a transmission in a cell earmarked with a 1 is not successful, it does a retransmission, but during that retransmission it asks the cells earmarked 2 and 3 to be silent. If on the other hand a cell earmarked 2 needs to do a retransmission, it does so in the time slots in which cells number 2 can do a surrounding reservation. And in that way we can stabilize this system and optimize the throughput. It is an idea inspired by the University of California, Berkeley project called the InfoPad on wireless multimedia, where we recognize that we need to talk about the performance of a packet-switched cellular network for wireless data communication, published in the journal Wireless Networks. And the whole discussion there is available, where I pitch that the optimization of packet-switched cellular networks is different from thinking of a phone call and preserving a good quality during that call all the time for a particular subscriber who may be in a bad position. Is this idea used? Well, surprisingly, in LiFi, in optical wireless communication. There we do have systems within one office, for instance a system offered by Signify, and there is a TDMA scheme. There are time slots defined according to the ITU G9991 standard. Now, multiple base stations share all these time slots. They have a common knowledge of where the time slots are. They can transmit in every time slot, but there could be an interference control where at some moments of time a particular area, a particular access points get the right to transmit and the surrounding area is kept silent. So it's a dynamic extension of TDMA, spatial TDMA. And I believe that spatial extensions to packet switching could be pretty interesting. And I already pitched that in 1995. But I do believe that particularly with the new design of cellular systems, but also new indoor systems or optical wireless communication systems, we can use these spatial protocols to improve the performance. And as I strongly believe, the delays in the network can really be made much smaller by smartly managing interference rather than rigidly having cellular reuse patterns.